So have 6 kBT. 6 mode, then you will have 6 times of the kBT. Okay. So U, the total energy, equal to 3 mode of the freedom times number of the atom times the average thermal energy per atom per degree. Okay, then we have U. So in the beginning of this chapter, I introduced you to how to get the CV, right? So the specific heat capacity equal to dU over dt at constant volume. So we simply differentiate this U over dt. So du over dt, we simply take out this T lah. So du over dt equal to specific heat. Then this specific heat equal to 3N kb. This is what we get from the classical theory. Does this classical theory make sense? Yes, partially, especially at the high temperature. Okay, so the specific heat is constant for all temperature. You see this equation. Specific heat equal to 3N kb. It don't have any parameter like T. So that means that at any temperature, you will get the same specific heat. And of course, like we know, this is not correct for all temperature. Okay, so the classical theory suggests that the CV equal to 3N kb for all temperature. Okay, so this is the classical result, the result from the classical theory. However, from the experimental result, we find that it actually look like this. Okay, so this is the classical result, and this is the experimental result. So we can observe here that at high temperature, this classical theory actually work well, but at low temperature, no, there's a big difference. Okay, that's a big difference. So from experiment, it's known that as T approaching 0, T approaching 0 means very, very low temperature lah, at this region lah. The CV also go to 0. So you can see the heat capacity, the specific heat capacity also goes to 0. According to the relation that CV proportional to T power of 3 for insulator, and then CV proportional to T for metal. So for superconductor, the CV will change at the fastest rate as T as compared to metal. I'm not sure whether you know what is superconductor or not, but if you are from pure physics program, then I will introduce you this term in solid state physics too. Okay, it's a very interesting subject. So we come back to the classical theory that we obtained just now. This is the equation that we obtained. So this solution or this classical theory is not accurate for CV at low temperature. Okay, from low temperature you can see there's a big difference. Okay, however, when you increase the temperature, then the difference becomes smaller and smaller. Eventually, they are very near to each other. Okay, I mean the experimental result and the classical theory result fit each other at high temperature, but at low temperature it's not correct. So that means that this Dulong-Pettit classical theory may not work well. It's not perfect, especially at the low temperature. So we have another scientist. His name is Albert Einstein. He proposed another model. Okay, so this is the second model for this specific heat capacity. So we have studied the second model. The first model is the classical one, Dulong and Pettit, and which does not work well, especially at low temperature. So now this Albert Einstein said, okay, it doesn't work well, so I want to improve the previous classical theory. So he assumed 3 things. Okay, Einstein assumed 3 things when he worked on this heat capacity of solid. The first thing is that he assumed that each solid was composed of a lattice structure that consisting of n atoms. And then each atom can move independently in 3 dimensions within the lattice, and it has 3 degrees of freedom. This means that the entire lattice vibration motion could be described by a total of 3n motion or 3 or degree of freedom. I mean 3n degree of freedom lah. And this one is correct. Okay, why is correct? We know that in the solid that composed of n atom, each atom have 3 degree of freedom. Yeah, we agree with that. So this first assumption is correct. Second assumption, she said that the atom inside the solid did not interact with each other. So let's say I have 3 atoms in the solid. So when I hit this atom will move, but the rest of the atom will not move. So this assumption is not correct. Okay, not correct. Why is not correct? Because we know that all the atoms or all lattice points are linked or bonded by the chemical binding. So when one atom move, then the nearest neighbor will also be affected. So the second assumption is not correct. Then the third assumption, he said that all the atoms inside the solid vibrate at the same frequency. Okay, so this is also not correct. So based on 3 assumptions that made by the Einstein, only the first one is correct, the second one and the third one is not correct. And therefore, this Einstein model also failed to explain the specific heat capacity of the solid. Okay, but anyhow, since he also contributed to this subject, so we also include his model in our lecture. Okay, Einstein's first point is accurate. This is regarding the number of atoms with the all atoms have 3 degrees of freedom. So why is correct or accurate? Because the experimental data supported his hypothesis. However, his second point is not correct because the atom inside the solid, if the atom inside the solid could not interact, then sound cannot propagate through it. Okay, we know that sound can propagate through the solid state, right? So if the first atom does not pass the frequency to the second one, then sound cannot propagate through the solid. So the second point is not correct. For the example, a tuning fork atom, when trapped, it will interact with one another and create sound which travel through the air to the listener ear, like this one. This actually proves that the atom inside the solid can interact, and it's also proved that the second assumption of the Einstein is not correct. Okay, so atoms also interact in the solid when they are heated. So when you heat, let's say you heat the iron from one end, then the heat would be transferred from one end to the other end. Why the heat can be transferred from one end to the other end? Because the first atom passed the energy to the second atom, the second atom passed the heat to the third atom, and so on and so on. So the atom actually interact with each other. Okay. So take for example a frying pan. If the pan is heated on one side, the heat will transfer through the metal, effectively warming the entire pan. So molecules that make up the frying pan interact to transfer the heat. Much in the same way, the oscillator in the solid interact when the energy is added to the system. So to the extent of this interaction lead to the physically observed heat capacity. So in this session, we're going to discuss the model of Einstein, okay, for the CV, the specific heat capacity. So within the Einstein model, the density of state is approximately by a delta function of some frequency omega e. This model is based on the quantum theory whereby each atom is replaced by 3 linear harmonic oscillator and representing the 3 degree of freedom. Therefore, for a solid with n atom, then we will have 3 n of the oscillator. Okay, so previously we considered that each atom vibrate in 3 degrees, but now Einstein assumed that each atom is actually converted each atom into the 3 vibrator. Okay, because each atom can vibrate in 3 degrees, so it's just consider it had the 3 oscillator. Then if you have n atom, then you have 3n oscillator. So the oscillators are assumed to be independent of each other, but have the same frequency.